Derivatives of standard functions. Hello everyone. Let's begin our lesson on the derivatives of standard functions. To start, let's look back at what we have already covered. In our previous sections, we explored the fundamental definition of a derivative using limits, a method we know as the first principle. Now, while the first principle is theoretically essential, because it provides the foundation for how derivatives work, you will find that calculating the derivative of every single function using limits is incredibly time-consuming and can become quite complex. To streamline this process and make our calculations more efficient, mathematicians have derived a set of standard formulas for the most common types of functions. The beauty of these formulas is that they allow us to find the derivative of a function almost instantaneously. Over the next few slides, we will examine these shortcuts in detail, beginning with the power rule and then moving on to trigonometric functions. The power rule. Now that we have established why using the first principle for every problem is too time-consuming, let's move on to our first and most frequently used shortcut, the power rule. This rule is specifically used to differentiate functions where the variable x is raised to a constant power, which we represent as n. Let's look at the formula. The derivative of x to the power of n with respect to x is equal to n times x to the power of n minus 1. To ensure you apply this correctly, I want you to follow this simple three-step process. First, identify the exponent. Simply look at the power n to which the variable x is raised. Second, bring down the power. This means you take that current exponent n and multiply it by the entire term. And finally, subtract 1. You reduce the original exponent by 1 to find the new power of x. Once you are comfortable with these steps, you will find that you can differentiate power functions almost instantaneously. Let's move to the next slide to see a practical example of this in action. Example of applying the power rule. Now that we have established the theory behind the power rule, let us look at a practical example to see how it is applied. We want to find the derivative of the function f of x equals x to the power of 5. First, we begin with step 1, where we identify the exponent. In this specific function, the exponent n is equal to 5. Moving to step 2, we apply the rule by bringing that exponent down to the front of the term. This means we multiply the variable by 5, which gives us 5 times x. Next, in step 3, we must reduce the original exponent by 1. So, we subtract 1 from 5, resulting in 5 times x to the power of 5 minus 1. Finally, by simplifying the exponent, we arrive at our result. The derivative of x to the power of 5 is 5x to the power of 4. As you can see, this process is much faster than using the first principle we discussed earlier. Once you are comfortable with this power-based approach, we will move on to see how derivatives work for trigonometric functions. Derivatives of trigonometric functions. Now that we have a firm grasp of the power rule, let us move on to another essential set of standard derivatives, the trigonometric functions. Unlike the power functions we just discussed, trigonometric functions are periodic, which means they repeat their values in regular intervals. Because of this nature, their rates of change, or their derivatives, also follow very specific, predictable patterns. For the grade 12 curriculum, there are 3 primary trigonometric derivatives that you must master, which we will cover in detail over the next few slides. The sine function. Now that we have introduced the concept of trigonometric derivatives, let's examine the first and most fundamental one, the sine function. As you can see on the slide, the derivative of sine x is simply cosine x. To put this into formal mathematical notation, we say that the derivative of sine x with respect to x equals cosine x. This is a straightforward relationship to remember, and it serves as the foundation for the other trigonometric derivatives we will discuss in the next few slides. The cosine function. Now, let's move on to the cosine function. The derivative of cosine x is negative sine x. I want you to pay close attention here. Unlike the sine function we just discussed in the previous slide, the derivative of cosine introduces a negative sign. This is a crucial detail that is very easy to overlook, so make sure you note this change. To put this into a formal mathematical statement, the derivative with respect to x of cosine x equals negative sine x. The tangent function. Now that we have covered the sine and cosine functions, let us move on to the third primary trigonometric derivative, the tangent function. As you can see here, the derivative of tangent of x is secant squared of x. To express this in formal mathematical notation, the derivative with respect to x of tangent of x equals secant squared of x. Please take a moment to memorize this result, as it is a standard formula that will save you from having to use the first principle. Once you are comfortable with these trigonometric rules, we will move forward to see how these derivatives are applied in real-world scenarios, specifically within the physics of motion. Real-world application, physics of motion. Now that we have covered the standard formulas for differentiation, let's look at how these mathematical tools are applied in the real world, specifically in the field of physics. First, consider an object moving in a straight line. In many physics problems, the position of this object is described using a power function, very similar to the ones we just practiced using the power rule. This is where the concept of the derivative becomes truly useful. When we take the derivative of the position function with respect to time, we are calculating the rate of change of that position. In physical terms, this result gives us the velocity of the object. Essentially, if you know the function for where an object is, the derivative tells you how fast it is moving. Let's move to the next slide, where we will apply this concept to a specific scenario. Scenario for velocity calculation. Now, let's put the theory we just discussed into practice with a real-world scenario. Imagine we have a particle whose position at any given time, t, is described by the function s of t equals 3t squared. Our objective here is to determine the velocity, v of t, at any point in time. To do this, we will follow a step-by-step calculation. First, we must identify the mathematical relationship between position and velocity. As we mentioned in the previous slide, velocity is defined as the derivative of the position function with respect to time. In mathematical terms, v of t equals ds over dt. Next, we set up the derivative by substituting our specific position function into the formula. This gives us v of t equals the derivative with respect to t of 3t squared. To solve this, we apply the constant multiple rule. This means we can keep the constant coefficient, which is 3, aside for a moment and focus solely on differentiating the variable part, t squared. Now we apply the power rule that we mastered in the earlier slides. To differentiate t squared, we bring the exponent 2 down to the front and subtract 1 from the power. This gives us 2t to the power of 2 minus 1, which simplifies simply to 2t. Finally, we combine our results. We multiply the constant 3 by the derivative we just calculated, 2t. This results in v of t equals 3 times 2t, which simplifies to 6t. We will now move to the next slide to finalize our conclusion on this velocity calculation. Conclusion on velocity. Therefore, based on the step-by-step calculation we just performed, we can conclude that the velocity of the particle is 6t. This result demonstrates exactly how the power rule we discussed earlier allows us to transition from a position function to a velocity function in a real-world physics context. Now that we have seen this application in action, let us move forward to review the key takeaways of this lesson. Key takeaways. Now that we have seen how these rules apply to both theoretical examples and real-world physics scenarios, let us summarize the key takeaways from this lesson. First, let's revisit the power rule. As we have seen, the derivative of x to the power of n is equal to n times x to the power of n minus 1. It is important to remember that this rule is versatile. It applies to any real number n, whether that exponent is a positive integer, a negative number, or even a fraction. Next, let's recap the trigonometric derivatives we covered. Remember that the derivative of sine x is positive cosine x. However, be very careful with the cosine function, as its derivative is negative sine x. The distinction in the sign is a crucial detail to keep in mind. Additionally, we noted that the derivative of tangent x results in the square of the secant function, which we write as secant squared x. Finally, the overarching goal of learning these standard derivatives is efficiency. By mastering these formulas, we eliminate the need to use the complex and time-consuming limit definition, the first principle that we discussed at the very beginning of this session. Now, before we conclude, let's look at some common pitfalls to ensure you don't make these mistakes in your assignments. Common mistakes to avoid. Now that we have covered the standard formulas and seen how they apply to real-world physics, let's conclude by looking at some common mistakes to avoid so you can ensure your calculations are accurate. First, let's address the sign error in cosine. As we discussed in the trigonometric section, it is very common for students to forget the negative sign when differentiating. Please be mindful that the derivative of cosine x is negative sine x, and not simply sine x. Second, let's revisit the power rule. A frequent error beginners make is subtracting 1 from the exponent, but forgetting to multiply the entire term by that original exponent. For example, if you are finding the derivative of x cubed, an incorrect approach would be to simply write x squared. The correct result, following the steps we practiced earlier, is 3x squared. Finally, be careful not to confuse constants with variables. It is essential to remember that the derivative of a constant, for instance, the derivative of 5, is always 0, as constants do not change. In contrast, the derivative of a linear variable, such as x, is always 1. Keep these points in mind, and you will be well equipped to apply these standard derivatives confidently.